we're online now. Welcome everybody. Thank you for being here. So we're pretty excited to have Danupon Nanongkai give a talk on TCS Plus. Before I introduce the speaker, I'd like to introduce the groups. So I'm gonna go around. First, we've got Andre with a group from MPII. Hi. Then we've got Benjamin Miller with a group from UW Madison. And Irfan with a group from Indiana University Bloomington. Hi. Fangye with a group from the University of Michigan. Then we've got Caltech. Hi. Zhang Yang from Virginia Commonwealth. We've got K. Gopalakrishnan from East Carolina University. Mark Selke from Cambridge University. So next we've got a group. Sorry, I'm kind of lost.
Yeah.
Okay, yeah. Hi. So I'm kind of lost about which group you are. We also okay. We've got Siddharth from the University of California, Irvine. They present. Hi. We've got Sarachai from Michigan State University. We've got the University of Toronto with Chris Carvasilis. Yes, we've got Yasamin from Johns Hopkins University, and of course we've got Danupon that's going to speak about the distributed all-pair shortest path exactly. So the next few scheduled talks are going to be, as usual, 2 weeks from now and 4 weeks from now. So the first one will be Michael Kearns from UPenn, and the second one will be Leonard Schulman. And again, I would like to encourage you to ask questions during the talk after you unmute yourself. Okay, so without too much more further ado, so again, we're very excited to have Danupon give a talk on TCS Plus. Danupon is currently a professor at KTH in Sweden. He got his PhD from Georgia Tech in 2011 and was advised by Richard Lipton, and has been doing a lot of great work on graph algorithms and distributed and dynamic graph algorithms. Today he's going to tell us about a recent result from Fox 17 on computing all-pair shortest paths in the distributed setting, and exactly.
Should it be my turn?
Yeah, sorry.
Oh, all right. So thank you for the introduction. Thank you for having me here, and thank you for being here. Yeah, so today I will talk about distributed shortest path, all-pair shortest path. And I guess you know what I mean by exactly from the abstract. By the way, I just realized that my video is not super fast, so I have another one down here, so you could see one of them. All right. So today, this talk will be about the problem is called exact all-pair shortest paths on distributed networks, and in particular, we will look at the algorithm on a model called Conjecture model. And one point that I want to make here is that the state of the art for this problem is pretty simple, and I really hope that somebody will make more progress And so one open problem that I want just to leave to all of you now is, can we have an exact all patches path algorithm that is as fast as the approximate one? And the last point is, maybe you don't like all patches path problem and you want to think about other problems. So same problem. Can you approximate one for other problems in the distributed setting? So before I continue, I would like to say that please feel free to ask questions at any time. And I think one of my video is gone, but that should be fine. So feel free to ask questions at any time. And actually, please do ask questions so that I at least see your feedback. And if you can turn the video on, that would be pretty helpful for me. Okay. So here's the plan. So I will start with defining the problem and give you a little bit of a background. And then we will look at the history of the problem a little bit. And then the main part, the technical part, will be explaining this our all-pair shortest path algorithm, which is Shen-Chung Huang and Tachpon Saranrat. And then I will just conclude with some final words. All right. Sorry, I have to switch. So let's start with the problem. And I will divide this into 3 parts. I will define the model called congest, and then we will get some warm-ups with some problems, and then we will jump to our own problem. So just to make sure to get some feedback a little bit from you. So can you let me know if you know already what congest is? Can you maybe raise your hand? I can probably see your video. Okay, maybe one group out of many groups. So yeah, if you haven't seen it before, here is my way of viewing it. So you just think of a network that is modeled by a graph. And there will be 2 parameters that are usually important when we want to analyze the complexity here. One of the nodes, and the other one is D, which we usually call hop diameter. So this is for example, you have a node to any other node in 2 hops. Okay, so this is a weighted graph, but the diameter we would always we will usually refer to hop diameter, which means you omit the weights. So these will be 2 parameters, and now as I said, this is like the network of computers. So every computer or every node has its own information. So in the beginning, every node kind of know how it is connected to other nodes, to the rest of the world. For example, node number 4 here knows that it's connected to 1, 3, and 6 with this weight 4, 1, and 1. But it doesn't know anything else. Local information. And in the end, they want to be able to compute something together. You can pick your favorite problem now. And they want to do it as fast or as efficient as they can. So what does it mean by efficient? So there are quite a few ways to analyze the complexity of algorithms on this model. One complexity that I will focus on today is called time complexity, or sometimes I usually call it number of days and nights, as follows. So you imagine that you start with day and night. Every day in the morning, everyone gets to send log n bits of messages to everyone else. Picture I just, but you can actually send log n bits. And then in the evening, the message arrives. And at night, everyone got the message and do their own local computation, meaning that they cannot talk to each other anymore. But we will assume that they have a free computation, which means that they can solve any problem they want. If they want to solve NP-hard problem, that's fine. Okay?
So, Danupon, just
Yes.
a small comment. Apparently, the connection is a bit spotty. I don't know if it's just on my side, but maybe try to remove the VLC video. That might solve it. In case that's what
Okay.
causes it. Yeah, that's. Oh, sorry about the interruption.
No problem. I need to find a way to remove it. 1 second. Is it better now?
Yeah, it looks pretty good. Thanks.
Okay. Okay. Oh, one more thing. Okay, so now so I guess I just already said that any calculation can be done in one night, and then the next day again, every node send a message, log n bit message to everyone, and then again at night in the evening, message arrives at night. They do local computation again. So the computation goes on like this, days and nights. And if you can finish whatever you want in 3 days, then we will say that the time complexity is going to be T. Okay, so if this is not clear, we will see some example. But first, let me make some remarks. First of all, this is called congest model, and you may imagine that there are many other models in distributed computing. For example, one model that probably you see when you go to Foxtalk is called local model, when we have no limit per day. And distributed computing, is more than that. Usually, other model, one assumption that we usually share is that we have free local computation, and we only count for communication. And you can see that the congest model is like that too. So number of days that I mentioned is usually actually called number of rounds. And in this model, there are actually, I make many assumptions. We have global clock, which means that everyone wake up at the same time, and they get to send message at the same time. No failure. If you send a message, it will arrive, and no delays. If you send a message, it will arrive in the end of the day. And we will make assumption as though that everyone has a unique ID, meaning that everyone has a number that is different from other, and it will be N. And as I said, free internal computation. All these assumptions were made just so we can focus on one issue for today, which is the congestion issue. And maybe some of you might ask, can we assume that we know N and D because it might make our life much simpler? And yes, you can at least assume that that is the case approximately. And the last thing is that in this talk, I will ignore logarithmic terms most of the time. So if somewhere you think it has to be there, I think you will be right. So maybe this is a good point before I show you some warm-up question. Any question for now? I guess not. Then I'll move on. So now I will give some warm-up questions. So the first question is called unweighted ST shortest paths. So here's the problem. So you have two spatial nodes, S and T. And in the end, what you want to know, and this graph is unweighted, by the way. In the end, you want S to say out like the distance to T, T to say out the distance to S. For example, in this case, T should answer 2. Okay, so that's a question. Now, if you just think for maybe 10 seconds, you probably realize that there's a simple algorithm for this, and it just takes diameter time. If you don't see it yet, here it is. So basically, you just run breadth first search algorithm, which looks like this. In the first day, the first node S will start the DFS, the breadth first search algorithm. So it basically just tell everyone that its distance is 0 because it's the source itself. And then at night, the neighboring node will be able to compute its distance. So now they will say that their distance is 1, which will be announced the next day. And then at night again, the message arrives, then the neighbor of S will know that their distance is 2. And you keep repeating this. You can see that in diameter time, everyone will be able to say the distance to S, right? And then they're done. So in D rounds, everyone can say the distance. In particular, D can say that its distance to S is 2. Any question about this one? So if not, so yeah, and it turns out that this is the best you can do as well. So you just need the routes or the time. Now let's make a problem a little bit harder. So next problem will be unweighted all pairs shortest paths. Still unweighted. So what is the goal? The goal is that every node should be able to say in the end, what is its distance to every other node. For example, here node number 6 should be able to say that its distance to 1 is 2, to node number 1 is 2. Distance to node number 2 is also 2, and so on. Okay? And let me emphasize that every node just has to know its own distance to everyone else, but not the distance between every pair. That is a different problem. Okay, now what can we do? Maybe I'll just give you 5 seconds to guess what is the running time you will need here. So one simple algorithm that maybe you will think of is running the breadth first search tree from every node. So every node just run breadth first search tree. Does it work? One problem that we have to worry a bit is that maybe there will be some conflict between algorithms. Meaning the following. Look at this example. If you run breadth first search from 1, 2, and 4, 3 nodes, in the second round of these, when you run these 3 algorithms at the same time, you will send, node number 3. You have to tell node number 6 that its distance from 1, 2, and 4 is 3 at the same time. So it has to send 3 messages. And you can imagine that if you have more nodes, it might have to send more. And this would be a problem if we have too many nodes, because in one round, you should be able to send only log n bits through an edge. But you don't have to worry about it. So one point I would like to make here is that all you have to care is the total number of congestion. I will just call it total congestion. What do we mean by this? So there's one pretty general theorem by Ghaffari from PODC 2015. And actually, if you just want to talk about all pair shortest path, you just need something simpler, which is by Layton, Mack, and Rao. It's called random delay technique. So the theorem says the following. So if you want to run many distributed algorithms in parallel at the same time, and now the congestion to be, the upper bound, when you look at overall algorithm, over all the rounds, all the time together, how many bits have you seen through an edge? That is congestion. Okay, let me read this out. Overall algorithms and round, the congestion, we see at most congestion bits sent through each edge. So if we define the congestion this way, and please remember this notion because it will be useful to understand our algorithm later. So then if you define it this way, then we can construct a randomized algorithm with the running time or number of congestion plus t, where t is the time of the slowest algorithm. So basically, if you run many algorithms at the same time, what will slow you down is the slowest algorithm among many algorithms.
Danupon, the question.
Yes.
Hello?
Yes, Gopal.
Danupon? Yeah, so this is, you're doing something heavyweight, right? We already know how to do this in OFN time, right? I think there's a paper by Roddy T. Pellak, they do it even deterministic OFN, right?
Yes. It's going to appear later. But
this Ghaffari thing is too heavyweight. It's too general.
But this heavy machinery will be useful for our algorithm later on. That's why I want to introduce it now. Okay, so it's good to remember it for now. Any other question? Okay, so I hope if you don't understand, please ask me. I can explain it again.
Oh, sorry, Danupon, sorry, I'm still asking. So the main thing, so the latent max Rao is just the congestion plus dilation, right? You just just you do the random delay, right? Is that the thing?
Yes.
So, but there's a lock factor, or he removes the lock factor, Ghaffar?
Yeah, as I said, I always, ignore.
Oh, okay. So this is just random delay. You start the algorithm with some delay, and then that's it, right? Is that the
Yes.
same? Okay.
Yes. Yeah. So in the end, the trick is that you want to start different algorithms at different time, at different like random time.
Okay.
Okay. Yeah. And now just to make sure you understand this theorem, because it will be useful to understand algorithms later. As a corollary, now you can solve unweighted or pairwise path in O(n) time, because you are just running n breadth first search algorithms. And for each algorithm, every node we have to speak only once, if you recall how the breadth first search works. Congestion will be just n. So if you plug in this theorem, T will be d diameter, and congestion is n. So the total time you need is n. Any other question? Now I will move on. All right, so now our problem. Our problem is just similar to this unweighted or pairwise path, except that now the graph is weighted. So this is the graph, one example. And in this case, maybe the shortest path will look like this from 1 to 6. And again, every node knows this local information, how it's connected, what are the weights of the edges. And let me emphasize two things. First, the weights of the edges do not affect communication. So this weight between 1 and 4 of weight 4, although the weight is 4, the time you need to send a message from 1 to 4 is just one round or 1 day. And another assumption which typically made is that we typically assume that the edge weights is in the range 1, 2 to polynomial of n. So it's some integer that is not too big. And one advantage of this is that to send the whole weight, you just need 1 round, because you just need log n bits or big O of log n bits. Okay. So now what can we do with this problem? I will just start explaining a few algorithms that maybe you can try to come up on your own for now. One trivial algorithm is just to collect the whole network to one node. And since we assume that we can solve any problem in one node locally, so everything you can solve NP-complete problem if you want. And so how much time do you need to collect everything to one node? It's just congestion, right? Because again, you just imagine that you send the input, local information from everyone to one node. And then maybe there will be one edge that everything has to pass through. And that will cause congestion of number of edges. So that's the time that at least we should try to beat the number of edges. So now one question is, can we improve the trivial algorithm? So let me discuss 2 algorithms that we probably know from the textbook and see whether what we can say about them. So the first attempt, and I hope you remember this, because this is one subroutine that we will need later. So what if you run breadth first search from every node? So what do we mean by this? It means that I will just pretend that my graph is unweighted by subdividing the edges. So for example, the edge between 1 and 3, you have weight 3. So I just put 2 nodes in the middle so that I have 3 edges in between. And then I just run breadth first search, where in the first round, number 1 here just send to the neighboring red nodes instead of node far away. But you will realize soon that it's not hard to see that this algorithm is going to be bad. It's going to be too long if we have a large distance between some pair of nodes, because you really subdivide the edges. We don't have any good guarantee here. So another attempt, a second algorithm, is Bellman form. So the algorithm is pretty simple. Every time you learn about the distance of someone, you just tell that to your neighbors. So in the beginning, you just send out your own distance, which is 0. And then later, if you start knowing some distance, you tell that to neighbor. Let's look at example here. So maybe at some point, node number 6 here, node is distance to node number 1 through this red edge. So the distance will be 5. So he will tell this to everyone. He says 5. But maybe later on, he discovered a better path like this. Oh. Then he has to, again, announce the new path, which is 4. Okay? And maybe he has to do it again and again and again, right? And he has to do that for about what he learned about distance to node number 2 too. So he has to do the same thing for every pair, every node. And so what we can say, one thing we can say about this is that the change of the distance from 6 to 1, it will change only n times. And if you want to convince yourself quickly, just look at the shortest path 3 rooted at 1. The next round of the Bell-Manford, the node in the first layer of that tree will get the correct distance, and the next round it will be the next layer, and so on. So in the end, you can bound the total number of times that some node has to say something to be n squared, which means that we have a congestion of n squared. So conclusion is that if you just run Bell-Manford, you will need n square rounds, which again is disappointing, I guess, because it doesn't beat the number of edges, like, the trivial algorithm. If not, let me just summarize, and if you want to ask questions before we move on, just let me know. So summary of this part, I have introduced you the problem, and the main problem that we will look at is the distributed weighted all-pair shortest path. And I have shown you 2 algorithms as a warm-up that doesn't work. Multiple, running breadth-first search from every node. This works for an unweighted case, but not for the weighted case. And Bell-Manford algorithm, they don't beat the trivial algorithm. But as I said, please remember these are 2 algorithms. They will be useful later on. And in parallel things that will be useful to remember. First, the congestion, only the congestion matters. In the end, you just need to understand how long the algorithm takes and how much congestion it causes. And we have this algorithm that run multiple breadth-first search.
Hey, Danupon?
Yes.
I have a question. Could you go back to the previous slide? I was just wondering, how is the congestion n squared?
Oh, right. So if you look at node number 6, right? Mm-hmm. You just count how many times node number 6 has to say something out. Right. Okay. And the claim is that he has to send an update of his distance to node number 1 only n times.
Okay. Yeah.
Okay. So if you don't see that, just accept it as a fact. To do with the breadth-first search tree. Sorry, the shortest path tree. Mm-hmm. Okay. And now he has to send but he has to send an update of his distance to n other nodes. He has to do the same thing for distance from 2, distance from 3, and so on.
Right.
So in total, you will see he can speak out, at most n square time.
So he will update at most n squared times.
Yes.
And so this implies that the maximum amount of information in an edge is n squared?
Right, because every time, if you look at some edge, let's say edge between 4 and 6, right? When do you need to send some information on this edge? It's going to be when node number 6 says something or node number 4 says something, right? And node number 6, as I claim, is going to say something, which is when it wants to update its own distance.
Okay.
Does it make sense?
Yeah.
Yeah, and the same thing, node number 4 will say its own distance n square times.
Right.
Okay?
Okay, thanks.
No problem.
But just a quick clarification.
Yes.
But more accurately, it's n times some kind of s, right? Where s is the shortest path diameter, the distance, right?
Yes. So yes. So if you if you want to introduce another parameter, then it will be n times the depth of the shortest path tree, basically.
Yeah.
Yes.
Yeah, that's what
But
that's what
just
I'm
want
calling
to,
as that's what I'm calling as shortest path diameter. This yes.
right. Yes, but I don't want to introduce another parameter. Okay, so that's the conclusion of this part one. Now, if you don't have any other question, I will tell you a little bit of what happened so far. And there will be quite some information, but if you don't want to, bother with a lot of information, this slide should be enough for you. So basically what we know is that this problem requires omega of n time, even if you want to approximate the distance. And I will just tell you why soon. And also, if you allow approximation, you can actually match this running time of ON. So ON is the best you can do with 1 plus x1 approximation. But it turns out that if you want exact solution, the best we can do is n to the 5 over 4, which is going to be the next part of this talk. Now let me tell you a little bit about what happened. And my point is that everything is, I think the state of the art is pretty simple, at least on this page. So why do we have this omega n lower bound? Just think of this graph where you have a star and look at one particular node, node number 1 here. So now, how can one, and let's say that the weight of the edge from 1 to 2 is 0. So for one to be able to say the distance to everyone else, it means that it has to learn about the value of the edges of all other edges in this graph. And since these values are independent, it's not hard to argue that you will need n bits to send through the edge from 1 to 2. So this is an informal argument, but you can make it formal pretty easily. Okay, so ON is pretty obvious lower bound. And the upper bound is also not hard. So I already told you that there is this one idea that you pretend that the graph.
Danupan, just a clarification. Danupan, yes. Hello.
Yes.
Yes, but this omega n also follows from that diameter, right? The approximation. Probably not.
Yeah,
for any,
but then you have to talk about it's not for any approximation algorithm. First of all, if you talk about an unweighted graph. Does that answer your question, Gopal?
But even for that, let's keep it on. So, but even for the diameter shows the approximation even for unweighted graph, right?
Yes, but that's not for any approximation algorithm.
Oh, that's true. Yeah, that's yeah. Some constant.
And it's a little bit wrong. You don't need that, at least for the weighted case. But you are absolutely right. Okay, and upper bound, so I already told you before that you can just, one idea is to subdivide every edge by the weight, right? And then run breadth first search from everywhere. But that's a bad idea. However, if you are happy with some approximation algorithm, some errors, then it turns out to be a good idea. So let me just give you an example here. So look at this graph on the right, and now you see that I have this weight, 39. What if I change it to 40? And basically, what if I change every edge weight to a multiple of 10? And then I just subdivide the edge weight by this, by multiplicity of 10, for example. If the weight is 40 here, then I just put three nodes. So you have 4 edges here. And I run breadth first search algorithm. So instead of having 40, steps on this edge from 1 to 3, I just need 4 steps. So I can just save something up, okay? And by, balancing parameters correctly, you can just use this kind of trick to make sure that you don't have much error and the breadth first search algorithm can finish in ON rounds. So that's basically the idea. You just, by allowing some error, you can run breadth first search from every node. So any question about this part? So then, okay, now this is pretty much what you need to know about all pair choice part in the weighted case to start with. But now let me zoom out a little bit and talk about more general problems for other cases. First of all, let's talk about, this is the more complete problem of the all pair choice part problem. I already mentioned the weighted case here in the red case was already studied as well as Gopal pointed out. And you can also prove the lower bound of omega n. And in fact, it holds even for the simpler problem called the diameter. And even for some approximation algorithm, but not for any, it's just for some. And we have an upper bound, which is deterministic, and that matches the lower bound as well. So just to conclude, and also for the weighted case, you can get the deterministic algorithm as well. That is by Lensen and Pachamir. So basically, for the unweighted exact and for the weighted approx, in both worlds, you get tight upper bounds, deterministic. But for the weighted exact, for the green part here, at least up to 2016, we don't do than just the trivial algorithm where you collect everything to one node. Okay, that was the state of the art. And an obvious question is, can exact algorithm be as fast as, can we get ON time for the weighted exact case? And actually now let me zoom out even a bit more. And again, if this is too much information for you, feel free to sleep for a few minutes. I will wake you up. So if I zoom out a little bit more, you can actually ask the same question for many other problems. So what happened is that in the distributed setting, in this congest model, in the last 2 decades, we know quite a few upper and lower bounds. For the lower bound size, we know lower bound of basically 2 forms. Actually, we know a bit more now, but these are the common 2 forms. One is in the form of root n plus d, and it usually holds for even for some approximation algorithms. And this holds for example, single source shortest path, minimum spanning tree, and many others. And the other kind of running time is omega n. This is for all pair shortest path, diameter, and so on. And then if you now from the algorithmic side, from the algorithm's point of view, we have kind of tight approximation that has been developed in the last 10 years in the following sense. So for problems like single source shortest path, min cut, minimum spanning tree, and so on, we have root n plus d upper bound, but it's a 1 plus epsilon approximation. So pretty much it's matched the lower bound stated above. And for problems like all pair shortest path, and even diameter and so on, you have big O of n upper bound and 1 plus epsilon approximation, which match the lower bound above as well. So you can ask the same question: can exact algorithms be as fast as the approximate one for all these problems? Okay, and to me, asking question for all pair choice part is a good starting point because the literature seems much simpler than other problems. And what we know so far up to these days, that I will just that I will tell you in the next slides, is that we only know a bit, and only for the shortest path problem. So now let me zoom in again to the shortest path. And again, if this kind of confuse you, go sleep for a few minutes if it's too much information. So let me remind you what happened so far. So until 2016, we know that for single source shortest path, we have a lower bound of root n plus d, which hold even for approximation algorithm. For exact algorithm, however, the best we know is just Bell-Manford, which has ON time. And for all pair shortest path, the best lower bound is omega n, the best upper bound is ON for n is 1 plus epsilon approximation. The exact algorithm, we don't know anything. Now we start to know much more than in 2017. So first result is by Sankowski for single source shortest path. So he got this running time. You don't have to worry about it too much about exact what this means. But basically, this can be written as little of n, something smaller than running time of this kind, little n plus d. So it's getting closer to the what approximation algorithm looks like, but it doesn't match the lower bound. And then for the all-path shortest path, there are two independent results. One result is by Elkin, and the other one is by as I'm talking about this talk, Huang by me and Saranurag. So Elkin got n to the 5 over 3, which is a bit better than number of edges than the trivial algorithm. And we got n to the 5 over 4. This is the best algorithm so far. And I think one interesting thing about this result is that it's also the first paper that the scaling technique in the distributed setting. And because of that, there are later it kind of leads to two independent results for the single source shortest path. So these two, and I'm not going to go into much details, but currently the best algorithm is by this one, by Sebastian Krimiger and I. So a summary of this part. So we know a lot of quite tight approximation algorithms. And we have some progress on the exact shortest path problem. And the state of the art for all path shortest path is pretty simple right now. So I really hope that somebody can push further and get something better for all path shortest path problem. That would be the first open problem. And the other problem is, can you prove some gap between exact and approximation algorithms for some natural graph problems? And the last question is, can we get the running time of the kind little of n other problems like min cut, max flow, matching, and so on. So before I move on and explain our algorithm, maybe it's a good time for questions again. So I guess no question. So so then now I will start explaining the algorithm. I'm kind of the organizer, please correct me if I'm wrong, but I think I will have only 10 minutes. So I will just describe the algorithm briefly, just to give you how this looks like. So this is what we want to prove. Just one more time. So we want to show that this with all path shortest path, the exact weighted case can be solved in n to the 5 over 4 time. So and this part will be organized like this. So first I will talk about the scaling technique, which you probably have seen before, have heard of. I have mentioned it before. And then I will talk about two special cases that we should solve first. The first one is called H-hop, all path shortest path, and the second one is called reversing the knowledge. And then I will tell you how to put everything together. Start with the scaling technique. So as I said before, this technique was known for a long time from Fox, from 30 years ago. It was used in many classic centralized algorithms. And basically, you can think of it this way. It is a way to reduce a problem, a weighted problem, to an unweighted one with simpler weight. Actually, no, not unweighted, but something close to unweighted. It will have simpler weight structure. And the idea is that we will have many iterations. And in the ith iteration, we will look at the ith bit, or we will solve the problem at the ith bit. So this is one example here. So in the first iteration, you will look at the first bit. And then the next iteration, you will look at the second bit, and so on, of the weights. So this is a little bit more detailed example. Suppose I have only 2 bits in the graph, in the weights. So the weights is at most 3. In the first round, I just construct a new graph where I just pick the first bit here. And then I just solve all pair shortest path or single sort shortest path here. And then using some magic formula, I will look at the second to construct a new graph, but the graph now look a bit more complicated. It's a weighted graph, for example. And then you solve the problem on this graph. And you keep just repeating this. If there is a third bit, then you look at the third bit. You solve the problem on the third bit. And once you're done, now you just claim that the result will be just the shortest path 3 that you get in the last graph. For example, here in G2, this is the shortest path 3. So, you know, the blue, the thick edges here, shortest path 3. The claim is that that is the shortest path 3 in the original graph. Okay. So, how does the scaling helps? The idea is that you can see that the weight is pretty simpler compared to original graph. For example, if you look at the first iteration, you only have weight 0 and 1. So it's much simpler than the original case. And in other iterations, it may be more complicated, but something we can claim is this. You have, first of all, we have weighted diameter, ON, meaning that the distance between every pair of nodes will be at most n. Okay, you can see that this is trivially true for the first round where you have one, but it's also true for other rounds. But it also creates some complication. First of all, it creates the graph that you have to look at is going to be undirected in the sense that the weight from 2 nodes, from I to j, will be different for the weight from j to I. You can call it asymmetric or directed. And the weight might be 0, even if you start with a graph without weight 0. Okay, so from now, this is going to be what the scaling technique gives us. And so from now on, I'm just going to remember, we just have going to solve the problem on this structure. If this is too complicated for you, just assume that the graph is 0 and 1. But note that this is a bit too simplistic. So sometimes if you solve the problem on that case, it's not going to solve the problem on the general case. Any questions so far? I guess not. Okay, so now we know something about the scaling technique. Now I'm just going to tell you two special cases that we want to solve. So the first special case is called H-hop APSP. So the goal for H-hop APSP is that you just want to know the distance, but it's not between every pair, but between every pair such that the shortest path between them is at most h. So you have parameter h here. For example, let's look at this example quickly. So the shortest path from 1 to 6 in this graph is 4. But if I set h to be 3, then it means that 1 doesn't need to know the distance to node number 6. Okay? So this is a special case of the all pair shortest path, because if you solve all pair shortest path, you know the distance between every pair, right? And H-hop distance just asks for something less. It's just between pair that is not too far away in terms of shortest path. Okay, so what do we know about this problem? If you solve the problem naively, you can just you can just run Bellman-Ford for H rounds, and it's not hard to analyze that the running time of that Bellman-Ford algorithm will be nh. So I have some explanations, but since I'm running out of time, again, it has something to do with shortest path 3. Now, what we can show is that this problem can be solved in n-root h round. So we improve this dependency on parameter h a little bit more. Okay, and this alone actually gives you n-root n time already. So since I'm running out of time, I will just give you an idea quickly. The idea is that maybe let's just look at this graph. What you don't like about the graph that we are looking at right now is that you don't like zero edge weights. So what we are going to do is that we're just going to change 0 to something else. And then we just run breadth-first search tree from everywhere. And then we will look at use the fact that we are interested in the path, in shortest paths that has at most that the error that you're going to get is going to be small. In particular, we're going to have additive error of something called of root edge. And we can fix that error using Bellman-Ford algorithm. So you somehow kind of mix this breadth-first search tree with the Bellman-Ford algorithm to solve the problem faster. So that's the first part. I'm just going to skip detail. Yes.
Danupon, also don't feel too pressed by time. You can take a few more minutes if you want. We started like a few minutes late, and anyway, it's not a strict limit.
Oh, okay. Thank you for letting me know. That's great. Yeah. So, but can you raise your hand if you actually want to know about how we solve this more? I already said. Okay, good. I saw some. Okay. So let me go slowly. Okay. So imagine first that if you don't have zero edge weight, meaning that every weight is integral and is like 1, 2, 3, and so on, right? What you can do is you can just run breadth-first search tree from every node, and you can analyze the range time of that to be ON. Why is that? Because I know that the weighted diameter is ON. So if I just pretend that you have unweighted graph, you just run breadth-first search tree for ON rounds, and the congestion will be just ON. So in the end, you just need ON time, which is great. It's even better than what I claimed. But now we cannot run breadth-first search tree because of this zero edge weight. So what we're going to do is we're going to change it to something a bit small, and the right parameter turns out to be 1 over root h. And then we can just going to run breadth-first search again. If you look at the graph on the left side here, so now I change it to like the graph on the right side, and I'm going to subdivide every edge by a factor of 1 over root h. So if the edge weight is n before, like edge between 1 and 2, I will see like n root h nodes on this edge. And now I run breadth-first search tree here. So now the running time of the breadth-first search tree to go from node number 1 to the last node will be n root h, right? Actually, from 1 to 2 already, you need n root h. So now this step, when you run breadth-first search tree, you will need n root h time. And what does this breadth-first search tree give you is the distance in this new graph, which is not the real distance in the original graph, because you have some error. But since I introduced only very small weights on the zero weight edge, I can bound the error, at least for the small path. So I have this error of 1 over root h for each edge, and I'm interested in h edges, so the error will be just root h. And now I run Bellman-Ford. And if you recall, what does Bellman-Ford do? It tells you a node kind of broadcasts its distance every time it improves its own distance to someone else, right? But you know that you already have this, but that is pretty close to the real distance. So the node will not say something too often. In particular, it will say something only n root h time, and that's why we have n root h upper bound in the last step. So that's a rough.
Danupon, quick question, Danupon. Hello?
Yes, go on.
Yeah, so this is only for 0-1 weighted graph, this h of APST, you're doing it in n square root of h rounds. What about, I guess this is only for the first iteration in the scaling, right? Later, the weights are not 0-1, no?
Yeah, but if you look at this example that I just gave, right, it's also not 0-1, right? It's like you have n in the first edge. Right? So the important thing here is that you are only interested in shortest paths that contain h edges.
So the weights are not important?
The weights are important. The only important thing is that the total, the weighted diameter is the O of n to begin with.
What? Again, sorry, I didn't get you.
The weighted diameter is the O of n.
Oh, that's okay. Okay, so But why are you saying in your slide 0, 1 weighted graphs? You're only saying 0, 1.
Oh, I'm sorry. It's a typo. I should say that for if for 0, 1 weighted graph, it's easy to see and it works for general weight structure as well. Sorry.
But even in general, the difficulty is 0 weights.
Yes, because you cannot run breadth first search with 0 weight. It's gonna kill, you cannot make progress. It's not trivial to see that. But breadth first search, the idea is that you want to make progress all the time. 0 weight.
What about the arbitrary weights? Like there can be many classes of weights. So
yes,
even then it's an issue.
It's fine as long as the weighted diameter is open.
Okay, I mean that is the shortest part diameter. Is that the shortest part diameter?
The weighted diameter.
The weighted diameter is that the same as the shortest part diameter? That means the number of edges in the long,
no.
The number of ops.
The distance between every pair of nodes.
Yeah, the maximum number of ops in the diameter, right?
No. The distance between every pair.
You mean the weighted distance or the number of ops?
Weighted distance. So since I'm running out of time, let me take Gopal. We can let me take your question maybe later or offline. All right. Okay. So sorry. So
kind of brushed over before, but like.
Sorry. Did you say something?
Yeah, I mean, maybe the confusion is coming from like definitions that you talked about in the slide or two before, but we didn't.
Sorry.
We were trying to rush through.
Oh, sorry. Yeah. So, but I guess so when I say weighted diameter, it means that the distance, like the real distance between every pair. Okay. Yeah. Sorry. So if you have more questions about this case, maybe I can take it. Maybe after everyone we finish or something. So now let me just define another special case. So reversing the knowledge. It's a fresh problem. So even if you don't understand what happened before, you can still understand this case. So the problem is this. So it's called reverse rsync shortest paths. So in this setting, you just have rsync nodes. And we assume that every node V knows the distance Vt, basically the distance to the sinks. So for every sink T. So if you look at the picture, this node V and this sink T, we know the distance to T already. In the end, what happens is that T also know the distance to V. Okay. So again, why is this special case of all pair shortest path? Because if you solve all pair shortest path, T will automatically know the distance to V. So you don't even need this, extra knowledge. Okay. But now the question is, if we have this extra knowledge, can we do something better? And again, the trivial algorithm is just NR routes by just sending all these distance pair, like broadcasting. You can see that the congestion will be just NR. So we show that actually you can do a bit faster. You can do N root R. And since I'm running out of time again, let me just say quickly. So the main idea is that you want to send the distance through the shortest path, send this knowledge. But then maybe some node or some edge have to handle too many information. And in that case, we're just going to identify that edge and just broadcast the distance else. So we will identify roughly root R spatial nodes with a lot of congestion and handle that separately. And for nodes with small congestion, you don't need to worry too much. Okay, so here's a summary of this case, of these parts. So we have three tools. A scaling technique, which allow us to have simple weight structure. And in particular, the weighted diameter is ON. And we can solve the all-pair shortest path, which means we are interested in just shortest path with small number of edges. We can do it a little bit faster than trivial, faster than NH. And then we can solve the reverse knowledge or reverse RC shortest path problem a bit faster than trivial, which is n root r. And now you just combine all these steps together. Just the idea why we get this running time of n to the 5/4. The idea is this. This is not completely correct, but it's just intuition. So if you just run the algorithm naively, collect everything, and the first two tools together kind of give you the first improvement over this n, so it becomes root n here. And then the last two give another root improvement, so it becomes n to the 1/4 over here. So I will just now just state the algorithm quickly, and then I'll just skip to the conclusion. So the algorithm is you just have 4 steps. So you sample root n spatial nodes called centers. That's the usual thing you should do for the shortest path. And then you run these first two HCOP, all-pair shortest path. And then you run you broadcast the distance between every centers. Or reverse knowledge. And the last step, you have to run the first two again, but a modification of it called modified HCOP, all-pair shortest path. It might not make total sense to you why we do this. If I have 10 more minutes, I can explain it to you. But since I don't, let me skip the analysis and just jump to the conclusion.
So Danupon, hello.
Yes, Gopal.
Just a question. So this is the property of the scaling algorithm that the weighted diameter is O of n.
Yes, it came. That's what scaling gives you.
So regardless of the weights, regardless of what the weights are.
Of the original weights.
Huh?
Yeah, regardless of the weights.
Oh, regardless of the weights. And second is, what is the message complexity of an algorithm? It can be like m times the number of rounds.
I haven't analyzed it, but I would guess it's really a lot.
Right, it can be as much as m times the number of rounds, right? That's of course.
I guess so. It's just I didn't analyze it.
Okay.
All right.
Okay.
Okay. So okay. Conclusion. How did we solve this part? Basically, to me, it's like you just discover that scaling technique can be useful, and then there are some two special cases that turn out to be important, and we somehow hack away to get some improvement for two special cases. So an open question for you: can we at least solve these two special cases or one of them in ON time? Right now, I don't know how to do that. And how about single source shortest path? As I said, once you found out that scaling technique can be useful, the Gaffari and Lee can use it with some other techniques, can get some improvement. And I and Sebastian Kriniger get further improvement, but that came from viewing scaling technique from a different perspective. In particular, you should think of it as approximate distance, approximation algorithm, but with some constraint called no local improvement. I think it's pretty nice view. And if you want to know more, either read our paper or the original view actually came from Klein and Subramanian. So maybe you can read that as well. And we know a lot of tight approximation algorithms, but I think we still don't have much progress on understanding exact algorithm, especially shortest paths. So open problem, the first one, can you solve shortest path either, as well, as quick as the approximate one for single source and all pairs? And how about other problems? How about, do we know anything that is in between, that has running time between n and n squared? All pair shortest path right now is one candidate, but I'm not convinced that it will be the case. So we'll see. So thank you for your attention. Let me know if you have more questions.
Thanks. So yeah, if there are any questions, now is the time before we we go offline. Thanks for the talk.
So, what is the best for SSSP now? What is this new result?
Yeah, it's this one by this one, clinical, and it's the running time is complicated. You have 2 algorithms. So basically, it's the minimum between root ND and root ND to the 1/4 plus something.
Okay.
Other question?
Okay, we can also take questions offline afterwards if you want to stay and ask more. Before we do so, I'd like to mention that the next talk is going to be 2 weeks from now. Again, it's going to be Michael Kearns from UPenn. We had also 10 viewers on YouTube today. And again, before signing off, I'd like to thank again Danupon and also behind the scenes, people helping for TCS Plus, Anindya Day, Gautam Kamath, Ilya Rosenstein, Oded Regev, and Thomas Vidic, who is also here today.
Thank you.
And
Thank you.
We're gonna go offline now.